This is a typical plant breeding program. 100,000 plots, 100,000 different genotypes grown in the same place. This is actually one of our collaborators in New Zealand growing this trial. And I want to talk about the power of plant breeding because this is what's going to be very absolutely essential if we're going to meet our food demands in the future. How successful has plant breeding been over the last 20, 30, 40 or 50 years or so? I'm comparing the United Kingdom here, which is a rain-fed in the same way it is in Australia, but also it's cooler and much wetter than it is in Australia, with Australia itself. You can see there's very significant differences in grain yield of wheat here. But you can see that the yields are plateauing off. In other words, it looks like plant breeding has not been very effective for the last 20 years or so. Certainly in the case of the UK, where yields are plateauing, but also in Australia, where if you look back about the last 20 years or so, there is very, very little yield increase if you go after about here. So it does look as if yields are plateauing in Australia and maybe globally, or at least slowing down. But you can also see that plant breeding has been incredibly effective in the past. What is the trajectory of grain yield of our major food crops in relation to global demand for grain? The current trajectory, if you look at all of the yield increases that have been made for our major crops where there's been massive investment, such as wheat, such as rice, such as corn, it's about 0.5% growth per yield per year due to breeding. So about 0.5% per year. Is that going to be enough to feed the estimated 9 billion people by 2050? It's possible to work out, based on current growth in yield, how much extra food we're going to need to feed an extra 2 billion people in 2050, in the next, say, less than 40 years or so. If we are going to feed 9 billion people by 2050, then we're going to require a growth rate of between 1.16 and 1.3% per year. That range in variation is due to the uncertainty of biofuels. How much of the crop, how much of the grain crop is going to go into biofuels. So we basically need an extra 50% more yield than what we're producing today to feed 9 billion people in 2050. That 50% extra yield is made up of extra grain, which will be consumed as food, but also extra feed grain for the additional demand in animal protein, which is also going to come from maize, from wheat as well. So it's pretty grim when you look at the current trajectory based on the last 20, 30 and 40 years of effective or successful plant breeding with where we need to be in the future in 2050. Okay, pretty grim. What happens if, for example, there is a massive scientific breakthrough, some eureka moment that is going to change the course of our food production? Some way where suddenly we can get an extra 10, 20% more grain than what we can get today from a really major scientific breakthrough. What is that going to do? If we had that breakthrough in 2012, it takes a long time for that breakthrough to work its way through the regulatory systems, the proof of concept systems, the adoption by commercial breeding companies, the translation into commercial reality. And again, a massive breakthrough about 2012 takes about 15 years at a minimum to play out before it hits commercial reality. Once it hits commercial reality, you can start to lift up here, but you're going to be a long way behind the food or grain that we will require in 2050. So very grim. Can we meet our food requirements through other means? We may not be able to meet it through plant breeding. So is there more land? No. There's no more land. There's decreasing arable land for agriculture. We have less water resources for agriculture each year. Water resources, particularly in India and China, where massive use of water is used for food production, is declining. We've also got the reality of increasing cost of food and fertiliser, the increased demand of animal protein as our lifestyles are improving, as our lifestyles in developing countries improve as well, the uncertainty in biofuels, and there's also massive issues or difficulties in relation to the technology and the infrastructure in developing countries. So again, there are some really difficult issues that we need to face in the future. Superimposed on that, we have the uncertainties associated with climate change, and we have a major disinvestment in agricultural research. Why? Because food has been cheap. And so there's been a massive disinvestment in agricultural research, which means a decline in our capability as we move forward into the future. So, what are the big challenges going forward? What are the opportunities? Where should we be putting our funding now into that's going to make a difference in the future? What should we be focusing on? What are the big ticket items that could really make a big difference? The big bazooka of all is to improve photosynthesis. Photosynthesis is absolutely central to our existence, to food production, to the entire vegetation. But the process of photosynthesis is very inefficient. So the evolution of photosynthesis is not a terribly efficient process. But the really big breakthroughs are probably only going to come from the improvement in photosynthesis. This will increase yield, it will increase water use efficiency, it will increase nutrient use efficiency as well. And the process of photosynthesis is associated with the capture of light, the energy, the absorption of carbon dioxide from the air and water from the soil. It goes into the green leaves that produce the carbohydrates that we require in the future. This is the rate of photosynthesis of our present varieties, but can we get to a whole new level? Can we increase photosynthesis by 20%, 50% or whatever? What I've got here on this table over here is the predicted, there are a number of ways, a number of opportunities which are open to us to increase photosynthesis. And I've put the different traits that are possible on this side, the predicted increase for each of these factors in this area here. So if you can increase rubisco without the oxygenase effect, you can potentially double the carbon fixation and double the rate of photosynthesis. But how long is that going to take? It's going to be we're 25 years away before we even get proof of concept for the really big ticket items. Some of these are already underway, but others are some are underway at the moment, others are about 25 years away before we get proof of concept. If you take a minimum time to commercial reality, you have to really add 15 years onto that. It took 15 years for the green revolution that we had back in the 1960s to make its way through the proof of concept, through to delivery onto farmers' fields. 15 years for a very, very simple trait, which was to reduce the height of rice and wheat. These are complex, so it's going to take at least 15 years, but maybe we're going to be much smarter. So 15, 5 to 10 years away, 35 years away before we can make really big changes in photosynthesis. So there's no easy fixes here, there's no miracles here at all. A second major area which I think is going to be very important going into the future as well. We know what goes on above the ground. We can see what goes on above the ground with our crops. We can see how effective they are, how diseased they might be, how healthy they might be, what the architecture of the leaves are. We can take all sorts of measurements on the plants above ground. But what's going on below ground? We have very, very little idea of what's going on below ground. Yet, below ground is where all of the water is extracted for growth. We know very, very little about the processes of water extraction by roots. Below ground is where all the nutrients are absorbed from the soil, all the nitrogen, all the phosphorus, all the micronutrients are coming up from the soil, extracted by the roots. We know very, very little about the processes by which the plants are able to absorb these nutrients and to absorb them very effectively. Below ground is also where the soil acidity, where there's salinity, where there's hardness which the roots cannot penetrate, and it's also where there's a lot of soil-borne diseases which affect the plants as well, be they fungi or bacteria or viruses or whatever. There's a massive microflora underground as well, and we need to understand what's going on below ground if we're going to make further improvements in yield. So a big black box at the moment which we really have to get into to understand more of what's happening down below.